Hey everybody, sorry we're getting started a little late. Let me ask you to quiet down a little bit. Okay, so this is lecture 6. Lecture 6, we're going to talk about light, continue to talk about light, and talk about how we use light to figure out the elemental composition of the universe. I want to be a little bit precise because what I'm going to talk about at the end of this lecture is what the universe is made of, at least in terms of elements that are on the periodic table. And what we'll find out later in the course is that that composition, the elemental composition of the cosmos, is in fact just a sliver of what the universe is made of in a grander sense. And that everything we know about on Earth, all of the elements in the periodic table, all of the normal elements that we know about, are actually just a tiny, tiny sliver of the total mass energy budget of the universe at large. But today, I'm mostly just going to talk about more grounded stuff, the normal elements that we're familiar with. So as we talked about last time, light is sort of an interesting phenomenon, and it's useful to think a bit about what it is. Okay, when we use light to see, but light is actually a broader phenomenon than just the bit of the electromagnetic spectrum that we use to see. So as we talked about last time, light is electromagnetic radiation that carries energy. It travels at a speed of about 300,000 kilometers per second through empty space. But it travels at a different speed, it turns out, through other types of materials. So light travels more slowly through glass or water than it does through air. And it turns out that matters if you want to construct lenses or manipulate the paths of light as it travels through different materials. It also consists of photons. Although it's made up of, it has a wave-like character, it also has a particle-like character. And the photons are the things that carry the energy. You can think of it as the things that deliver the energy in light. And the energy of each photon in light depends on the wavelength of the light that you're talking about. So longer wavelength light, like radio waves, has low energy photons, and shorter wavelength light has very powerful photons. So gamma rays are made up of very powerful energetic photons. Just for a sense of scale here in nanometers, we talked about this last time, just to reorient ourselves. The visible light, the human eye can respond to things between about 400 nanometers and, let's say, 750 nanometers or so. That's the visible part of the spectrum, but it spreads out much farther than that. And at very short wavelengths, down below, let's say, 0.01 nanometers, that's when we're talking about gamma rays. And much longer wavelengths, up to sort of 100 meters or so, those are radio waves. AM radio waves are very large. Yeah?
You said if it goes through certain objects, the light can slow down because it goes through glass. Is there anything where it can go through it and actually go faster?
No. So the fastest light goes is traveling through a vacuum, at least that we understand, and that's the speed that we typically quote as the speed of light.
Okay.
So as far as we know, there's no sort of simple object that you can pass light through and it goes faster than that. So one of the things we talked about last time is the fact that hot objects, or in fact any object that has a temperature at all, is emitting electromagnetic radiation, is emitting light. What I want to start off today with is why do hot objects emit light? So why is it when you have hot lava bubbling out of the ground, why does it glow at all? Much less why does it glow orange or red? Why does it glow at all? What's going on? What is going on in this material that makes it emit this light? Does anyone know? So why does light come out of stuff? What's going on there? Well, to understand this, we need to go a bit deeper into what light is. So far, actually, I've been talking about light in a very descriptive way. But what's the origin of this light and what's going on here? As we talked about before, light is basically a wave. It acts like a wave, but it's a wave of what? Okay? So the waves that we're familiar with in day-to-day life are things like water waves. Okay? But I don't just say waves, I say water waves, right? It's a wave, a disturbance that's propagating through water. So you punch water and waves propagate from it. And what's going on at a microscopic level there is water molecules are pushed and they push other water molecules, and that creates a disturbance that sort of propagates along at some speed that has to do with the water. Sound waves, it's sort of the same kind of thing. A sound wave is a pressure wave. Okay, so if you vibrate a drum, that disturbance vibrates air molecules, and then that disturbance propagates along in the air. And the speed of sound through air is just the speed with which that propagation can move through the air. And it depends on the composition of the air. If you change the temperature of the air, it changes the speed of sound in air a little bit. So that's what sound waves are. Sound waves are propagating through air. If you take the air away, there's no sound. Okay? So even though it's really cool to watch Star Wars or whatever, and the Millennium Falcon's going along making a sound through space, that it would never happen, right? Because there's no air. So there's no air, there's no sound. But light's something else, right? Because light clearly propagates through empty space. We see the stars. So I was telling you light's a wave, but it's a wave of what? Like what's propagating? What's going on? Is it a disturbance? And in fact, the nature of light and understanding what the medium was that light was traveling through was this big question in, sort of 150 years ago in physics. What is the stuff that light's propagating through? What is it? It's a wave of what? Okay. Now we now understand it. In fact, it's not a wave propagating through anything. And that's one of the things that makes it different than what we're familiar with on Earth. I'll talk a bit more about this question of what light is propagating through when I talk about Einstein in a couple lectures. But it turns out that today, when we think about light propagating through a substance, it actually doesn't need a substance to propagate through. It is its own substance in some sense. Light, or electromagnetic radiation, as you can tell by its name, has something to do with electric phenomena, so electric charges. But it's also got that magnetic stuck on the end of it. So it also has something to do with magnetic fields. All right? So, if you have a charge, like a proton or an electron, anything that's got a charge, that will create an electric field. And what that really means is that there's a field around it. So if you bring another charge in, that other charge will either be attracted to that electron or repelled by the electron. Okay, so if you have an electron and you get another electron near it, will those two things repel each other or attract each other? Yeah, repel. So like charges repel, but if you have an electron and a proton's brought in, those things attract. And so one way of thinking about those forces, that a force of attraction or repulsion between those two things, is to instead just think about the electric field that's created by the electron. And that field affects protons differently than it does electrons, but it's still a field. So you can think of it as sort of a description of the phenomenon that's independent of the thing it's going to interact with. So that's an electric field. But magnets, in fact, also create fields. So we're familiar with magnets. Most of us have played with magnets, put them on our refrigerators. Okay, they create fields as well. And the thing that magnetic fields do, it turns out, is they deflect the paths of charged particles. So if you have a magnetic field and you have a charged particle moving through it, the charged particle will feel a force from the magnetic field and deflect it. In fact, the magnetic field of the Earth deflects charged particles coming at the Earth, and in some sense provides some protection of the Earth from these charged particles that might otherwise do more damage to us. All right. So, this idea of electricity and magnetism, these phenomena of magnets and electric charge, like static electricity, people have known about this for a long time. It's a day-to-day phenomenon, really. But understanding what it was and how they related was something entirely different. It turns out by wiggling charged particles, you can set up oscillations in the electric field. But that changing electric field, it turns out from experiments, you can show that that also creates a magnetic field. And vice versa, if you take a magnet and you spin it around or move it, you can do that to generate an electric field. You can create electricity that way. And in fact, this is a common way, this is the way electricity is generated. You can move around magnets. And in fact, what eventually people began to realize is that if you create a changing electric field, that generates a magnetic field. But if you generate a changing magnetic field, that comes back on itself and helps to create an electric field. So in some sense, when you create an electromagnetic wave, it's sort of like a self-sustaining wave that can propagate and do things. This was fundamentally figured out eventually by a Scottish physicist named James Clerk Maxwell. So the year is think of a year sometime around 1870. Okay. One of the four forces of nature is electromagnetism. Okay, so this phenomenon of electricity and magnetism, it turns out, is a fundamental force of nature. It's one of the four fundamental forces of nature, of which gravity is also one of those. Prior to Maxwell, the observed behavior of magnets that we know about, like compasses, people had compasses and things like that, and electricity, like say static electricity, or even all of the experiments on electricity that Ben Franklin is famous for. All that stuff was obviously known before then. But what Maxwell showed is that these are not independent things, and in fact they're related. And he proposed that electricity and magnetism and light itself, therefore, were all aspects of this same fundamental law. So the idea is that you have an electric field that's propagating in one direction and a magnetic field that's propagating in another direction, and that and a propagation of those paired fields is an electromagnetic wave. He, in fact, calculated the speed that such an electromagnetic wave would travel, and he came out with a number that was really close to the speed of light that had been observed independently, as I've talked about. And so for him, it was sort of this natural thing. He's like, wait a second, this stuff, this light that we use to see, this is just an electromagnetic wave. And it behaves in exactly the same way an electromagnetic wave would behave. And it just so happens to have a specific wavelength or frequency. Are there any questions about that? Yeah. No? Oh, okay. Any questions? So when a hot object is radiating, what's going on? So what is it when something is hot? What happens? So what does it mean? What are you doing to something if you heat it up? Yeah.
Speeding up the molecules.
Exactly, yeah. You're speeding up the molecules. So when you heat up something, you're making the molecules in that thing jiggle around faster. Okay? Now, given that these molecules have electrons and they have charged particles that make them up, if you jiggle them around, you then create these electric fields. When you jiggle around charged particles, that creates electric fields. That makes electric fields change. So you set up an electromagnetic wave. So the motion of these electrons create these light waves. And so in sort of a microscopic sense, that's what's going on. If the photons and molecules are in equilibrium with each other, in a sort of, let me just say that in sort of a qualitative way, if they sort of share energy and there's nothing, and it's a stable configuration, then the spectrum of light that will be emitted, and I'll talk about this in a bit, is called a black body spectrum. We mentioned the word black body last time. I'm mentioning it again now. It will emit light in a specific way that's called the black body spectrum. Now, in order to understand, what are you even talking about in terms of a black body spectrum? What does that even mean? You have to back up a little bit and talk about this idea of spectroscopy. So spectroscopy is a way of studying light sources or things that glow by sorting that light into its component colors. So, if you have a light bulb that's glowing in some way, you can imagine in the simplest scenario, you take that light bulb, you shine it through a prism, and that spreads the light out into all of its component colors. We talked about this before. And spectroscopy is studying how much light comes out at each color. So is most of the light coming out in red, or is it mostly coming out in yellow, or blue, or purple, or what? And more generally, it's not just colors you can see, but when light is spread out, when electromagnetic radiation is spread out, it's spread out over its wavelengths. And so you don't have to think about it in terms of the colors that your eyes see. A generalization of color is just looking at the wavelengths that it comes out at. Okay? So the spectrum of wavelengths is what you're looking at when you take light and shine it through a prism or another kind of device that spreads light out into its constituent wavelengths. And often what you do is you plot out the intensity, or how much light is coming out per wavelength, at each wavelength, as a function of those wavelengths. Now, I don't know if that sounds, you might see that and you're like, okay, well that's boring. Why would you do that? I see that, I get the idea of looking at a pretty prism rainbow, but then why would you then break it up in this quantitative way and study this? Well, it turns out you can learn a lot about something by doing this. Now, one of the things that you observe, that you see if you do this, is that if you take different sources, okay, that have different colors, have different temperatures, and so these different colors down here in these cartoons are representative of different temperatures of objects that you can measure, okay? And then you look and see what the spectra of these different sources are that have different temperatures. You see that the hotter the thing is, the more its spectrum is emitted in shorter wavelength light. So hotter objects tend to spit out their radiation in shorter wavelengths, and colder objects spit out their radiation in longer wavelengths. And you might think about this qualitatively as sort of making sense, that if it's hotter, the objects are jiggling back and forth faster. Okay? And then you might think, oh, well, that's, maybe that's going to be, higher frequency and therefore shorter wavelengths. You think about it qualitatively that way. It turns out that kind of approach doesn't work exactly, but it's I think it's a reasonable qualitative way to think about it. Okay? But this is just an observed fact, and they have very specific type of spectra that's called a black body spectrum, that if you know its temperature, basically that's all you need to predict exactly what this spectrum is, exactly how much light's coming out at each and every wavelength. And you can test this in the laboratory, right? So has anyone done this in a laboratory, like in high school or at UCI? Okay, a couple people have done this. Okay, so you can talk to them, they verify this actually works. Okay, so you can say, all right, you can do these tests in a laboratory that's very well understood and figure this out, and there's just a great, it's very well understood what the correlation is between the temperature and the spectrum. But given that that's observed, you can then say, oh, well, if this is just generally true, that means I don't have to actually be there with a thermometer to measure the temperature of something. As long as I can see the light from it, I can measure its temperature. Because all I got to do is take the light, break it up into colors, measure its spectrum, and then I know its temperature. Right? So in principle, I could determine whether or not you're running a fever if I had a detector that could then take all the radiation coming off of you, break it up into component colors, measure the black body spectrum, that would tell me your temperature. That's not how we do it, but I mean, you could in principle do it that way. And I should mention that not everything radiates like a perfect black body, and I'll come back to this later. But here are some things that emit light, at least some of the light that you see coming from them is like a black body, right? So the hot embers from a fire, hot lava, the surface of the sun looks a lot like a black body spectrum. Light bulbs and other things have spectra that basically look like black bodies to first approximation, so you can then define their temperatures in a very precise way. And in fact, that's actually how we define temperature now. If you measure the spectrum of something and fit a black body to it, you can then measure the temperature that way. And that's the most precise way to measure the temperature of something. So now that I've introduced this idea, let me be a bit more precise. A black body, this term black body, is actually a theoretical construct because it applies to for a very specific thing. Okay, so it's something, it's the simplest possible object that can give off radiation. In the sense that they absorb all radiation coming at them. They don't reflect anything. And that's why they're called black bodies, right? So not much light is reflected, or no light's reflected. And in fact, nothing's transmitted. So the only light you see coming from it is the light that's being given off because of its heat. And the atomic motions within this object cause it to emit energy, that is, emit light, in a way that depends only on its temperature. And here are some examples of black body spectra. So what's shown here is the brightness as a function of the wavelength of the light that's coming out. And if you have something that's very hot, like 7,500 Kelvin, it will emit its light, peaking somewhere in the blue, in the light blue, towards green. Whereas you have something cooler than that, say 4,500 Kelvin, it's moving into sort of the orange. But then again, there's light coming out in lots of wavelengths, and so there is a spectrum. But the peak of the intensity is coming out, for example, in this case, the 4,500 Kelvin case, is coming out in the orange or so. Are there any questions about that? Now, one way to describe what's going on here is with a simple law called Wien's law, which is shows the relationship, the mathematical relationship between the wavelength where this intensity spectrum peaks and the temperature of the object. And this is the formula. Okay? So the formula is that this T right here is the temperature of the thing you're looking at. And this lambda here is the peak wavelength where most of the light's coming out. So it's written in this way because this is actually a really easy way to use this formula. All right, there are other ways to write Wien's law. If you type Wien's law into Google, you'll get lots of different ways of writing it. But this is a very simple way of writing it because, for example, if the temperature of the thing is 10 to the 4 Kelvin, then I plug 10 to the 4 Kelvin in for T, this whole thing becomes as just 1, and the wavelength, the peak wavelength is at 3,000 angstroms. An angstrom is 10 to the minus 10 meters. Okay? If the temperature were 3 times 10 to the 4 Kelvin, then I plug that in. And then I'm left here in this parentheses is just 1/3. And then I'd have 3,000 angstroms divided by 1/3, or divided by 3, so it would be 1,000 angstroms. Now, as a point of detail, let me just also show you that you notice that these brightness curves go higher if the temperature is higher. So the bigger the temperature, the higher the brightness is. At almost any wavelength, actually. So the second thing you want to know is not just where most of the intensity is coming out, but how much energy is coming out in total. Okay, so like the normalization of these curves. So you can see there's much more light coming out of this thing at 7,500 Kelvin than there is at 4,500 Kelvin, even sort of independent of the wavelength you're looking at. So that doesn't have anything to do with color. That has more to do with brightness. Okay, and that's related to something called the Stefan-Boltzmann law, which is that the energy coming out per second emitted by a black body increases with the temperature, like the temperature to the fourth. So if you double the temperature, then the energy coming out per unit time goes like 2 to the 4. It's 2 to the 4 times higher. So 16 times higher. So hotter objects emit more energy per unit time than cooler objects. A lot more energy per unit time than cooler objects. And they also glow in bluer light, mostly. So they'll look bluer and they'll spit out more energy the hotter you are. Are there any questions about this? Yeah?
Can you explain one more time how to use Wien's?
I will. So the question is, can you explain one more time about how to use Wien's law? So let me give you an example of using Wien's law. Maybe this will help. So let's say we had a question and we wanted to know what the surface temperature of the sun was. Now, it's very hard to go to the sun and put a thermometer on the sun. That's not an easy thing to do. But according to what I've just talked to you about, that's not required. What's really required is you just take the light coming from the sun, you spread it out into wavelengths, and you measure its spectrum. All right? But let's just do an even simpler thing. What color is the sun?
Yellow.
Yellow. The sun is yellow. Okay? So we know roughly where it peaks. This isn't precise, but we roughly know its wavelength distribution is going to peak somewhere around yellow. Okay? Let's just posit that. And yellow light is somewhere around 6,000 angstroms. That's here. 600 nanometers or 6,000 angstroms. So let's say we wanted to use Wien's law, which is this, to figure out what the temperature of the sun was. So we're assuming that lambda max is 6,000 angstroms. And we know that that should equal 3,000 angstroms times 10 to the 4 Kelvin divided by whatever the temperature of the sun is. So then we can manipulate this equation to figure out what T is in terms of things that we know, lambda max and these other numbers. All right? So if I put T on the other side, this says that T is equal to 10 to the 4 Kelvin, it's just sitting there, times 3,000 angstroms, and then that's divided by now this, because I've divided both sides by lambda. So I divide both sides by lambda, and I multiply both sides by T, and I get this equation. It's the same thing. So then I say, is that clear? So then I say, I know what lambda max is. It's about 6,000 angstroms. So now in this parentheses, I just have 3,000 angstroms divided by 6,000 angstroms. That's 1/2. And 1/2 times 10 to the 4 is 5,000. So you get a rough surface temperature of the sun of 5,000 degrees. And that's about right. That's about how hot the surface temperature of that's about the surface temperature of the sun. Does that help? Okay. Any questions on this? Yeah.
I have a question. Is there an object that doesn't radiate like a black body?
Are there objects that don't radiate like black bodies? If you have objects that don't have really well-defined temperatures, they don't radiate like black bodies. So it's possible to have things that actually don't have well-defined temperatures. So you have to be in equilibrium to have a temperature, turns out. So like a single hydrogen atom floating through space does not have a temperature, for example. So you need some statistical conglomerate of something to have a characteristic temperature. But most things that you're familiar with in your day-to-day life do at least have some component of the light coming out of them that emits like a black body. Okay? But they're not perfect black bodies, and I'll get to that in a second. That's where I'm going now. Okay? Well, let's do another question. What's your spectrum? Okay? We all have some temperature. Okay? And all of our temperatures are somewhere around 98 degrees Fahrenheit, unless you're very ill, in which case you should leave. Okay? And that's about 300 Kelvin. All right. Is everyone clear with Kelvin? Are people familiar with the Kelvin temperature scale, or are you okay with it or no? Does anyone have any question about what I mean by Kelvin, what I'm even talking about? It's just a different temperature scale. It's like Celsius except 0. 0 Kelvin is like absolute 0. You can't get any colder than that. Okay. So room temperature then is like 270 Kelvin or something like that is cold, and 300 Kelvin is like, the temperature of our bodies. So we know what our temperature is, so we can just use this Wien's law equation to figure out where our peak spectrum is, where most of our light is being spit out at. So if the temperature is 300 K, I plug it in here. All right. I can do that math pretty easy because I got a 3 in the denominator and a 3 here. I can cancel those. And then I've got 1,000 times 10 to the 4 over 10 to the 2. And what you get is 90,000. 90,000? Oh, I did it more precisely. Anyway, you get a number like about 90,000. All right. Now, if our peak wavelength is coming out right around 90,000 angstroms, that is in the infrared. Okay, that's too long for us to see. We can't see anything longer than about 7,000 or 8,000 angstroms. That's about red light. That's as red as we can see. So this is redder than red. And what is infrared light and sort of common language? What's infrared radiation? What do we call that? Heat. It's heat, right? So this is the heat that we're emitting. That's why you burn calories by just sitting around. That's one reason why, right? You're just burning. You guys are all burning calories here, so you're having a great workout, just emitting your black body radiation. Okay. But let me ask you a question then. So we're emitting our light in the infrared. We can't see in the infrared. How can we see each other if our light's coming out in the infrared? How do we see each other?
Light's reflecting off of us.
Yeah, light's reflected off of us. And that means we are not perfect black bodies. Right? The fact that we can see each other is proof that we are not perfect black bodies. Because light's being reflected off of us, and the reflected light is a different spectrum than the radiated light. And the same is true in astronomy for astronomical objects, right? So while stars are hot things, typically like 5,000 degrees or so they're emitting light in the visible, planets orbiting around them are typically not that hot. So the Earth is emitting light. The Earth has some temperature, but it's mostly an infrared kind of temperature, okay, thankfully, right, or else it'd be very uncomfortable. And so if you were, for example, trying to study a planet around a distant star, what would you see coming off that planet? Well, first of all, you would see the light just reflected off the planet, right? So sunlight coming into the Earth, a lot of it's just reflected off by clouds and things. And then there's another component of the light that's coming from its own emission. So to first order, you would expect a bump from reflected light in the visible, and then another bump from the emitted light, the infrared light from the planet. And so if you were studying a planet and you just wanted to look at the light coming from it, you'd be learning about not only itself, its own temperature, but there'd be a second component in its spectrum that had to do with the reflected light from the star it was sitting around. Now the really hard part is, most of the time, in fact all the time, the normalization is not like this at all. Stars are so much brighter than the planets, right, that this thing is way up here. So even this tail that's coming down just completely swamps it, oftentimes. So, imaging planets around other stars is hard business. And, but anyway, these are the kind of things you have to think about if you're trying to do it. There's another observed blackbody curve that's very famous, and it's the temperature of the Big Bang, so the radiation that's left over from the Big Bang. If you look, and I'll talk about this in a later lecture, if you look all over space, just all over the sky, and you measure the temperature, it turns out that there is a component of radiation that's coming from everywhere that you look, that has a spectrum that looks like this. And in fact, it's a perfect blackbody spectrum at a temperature right around 3 degrees Kelvin. So it's very cold. And when people talk about the coldness of space, if you're going to assign a temperature to space itself, it would be this temperature. What this really is, it's light and energy that's left over from the Big Bang that's very, very cold. And in fact, it has almost a perfect black body spectrum. I've heard it said, and I don't know this for sure, that this is the most perfect black body spectrum that's ever been measured in a naturally occurring phenomenon. It's a perfect black body. And the amazing thing is it fits this black body curve so well, and the black body curve shape was something that was discovered in laboratories on Earth, you know, long ago, long before it was ever measured. And this is telling us something about the very creation of the universe. There's a lot of clues about what the universe has done over the course of its history, and it tells us something about how much the universe has expanded, how hot it was at early times, and there's a lot of information in here. But anyway, this is a black body curve of the universe itself. So the universe itself, in some broad sense, is emitting like a black body with a temperature of about 3 degrees. So this is an example of something that does have a well-defined temperature that you might not think would. So let's go back to the idea of perfect black bodies. I've told you this was the most perfect black body that's been observed. What about other things that seem more common? Why aren't they perfect black bodies, or what's going on? So, for example, a candle. That seems like a pretty simple thing. You light a candle, you shine its light through a prism, you spread it out. It actually looks more or less like a black body at first. You know, you look at it and grossly it does look like a black body. But there's interesting things going on. That if you break it up really finely in its component colors and component wavelengths, there's specific wavelengths that are brighter than others than you would otherwise think. These kind of things are known as emission lines now, okay, because they look like lines. That's why they're called emission lines. What is this? Does anyone know what this is? Yeah.
It's like when the electron's excited and it drops down a level and it's a photon at a specific wavelength.
Yeah, that's right. So we understand this now in an atomic way, and in fact quantum mechanical way. But it has something to do with the very structure of atoms themselves. That these are the emission signatures when electrons in an atom are in an excited state and they fall down to a less excited state and they spit out light. Okay. And in a more empirical sense, it turns out that if you take isolated elements, okay, let's say you take hydrogen and you get it hot and you just look at it. Okay. Hydrogen spits out light at a few very specific frequencies. And helium, on the other hand, also spits out light at very specific frequencies, but they're different frequencies. And in fact, all elements have their own code of spectral emission. And it's almost like a barcode. Okay? You read the barcode and it tells you what it is. All right? So you don't have to know how much the apple costs. You just, do its barcode and it tells you. So you don't have to know what a ball of gas is made of, in principle. You can just heat it up, look at the spectrum coming out of it, and you see its barcode, and you're like, oh, that's hydrogen. That's the spectrum of hydrogen. Or if you look at it and you see, oh, it's helium. In a more realistic sense, you could see a mixture of hydrogen and helium by just taking those two things and putting them together. Or if you have a lot more helium than hydrogen, you would make all the helium lines a lot brighter than the hydrogen one and then put them together, right? So you can imagine, because every single one of these elements has its own spectral signature, you can use this as a tool for figuring out what things are made of by just looking at their light. So you're not only learning, in principle then, this means you not only can learn about what the temperature of the sun is, but you can learn about what the sun is made of with this kind of technique. Does that make sense? Now, in practice, if you were to do experiments on this, what tends to happen is, let's say you have a light source that is a perfect black body. It's just an example of using this kind of technique. You would take that light, spread it out into its spectrum, and you'd get some black body curve. But then let's say you took that same light source and put a cold gas cloud in front of it that was, for example, made of hydrogen. The light shines through it. It turns out hydrogen likes to catch very particular type of photons. Okay? Hydrogen only wants to, one of the things it really likes to do is catch photons that allows its electrons to move up one energy level, for example. So that defines a very particular type of photon it wants to catch and hold on to. And then later that electron will fall down and it'll spit something out. So for example, along this spectrum, you can imagine it was this color. So all the light that's coming in that happens to be this color, this specific wavelength, that hydrogen will absorb and it'll let everything else go by. So then, if you look at a spectrum of a source and you see this, you'd say, oh, that it must be shining through hydrogen, for example. Does that make sense? Even if you can't see this stuff, you can tell it's there because you've seen this absorption. Another possibility is, imagine you don't have the light source at all. And something, or imagine, for example, you have a telescope that's here, and you're just looking at light coming from this direction. There's no light source behind it. There's another thing over here that you're not looking at and can't see that's shown through this gas. Okay, just like this. And it's caught all the light that was this color. But now that electron is in an excited state associated with that color, with that energy photon. And a little while later, it'll just fall back down to its, say, ground state and spit that photon out. And it'll spit out the same color it likes to catch. There's a certain symmetry there. And so it'll spit out that same color, and you'll see it spitting out over here. Now you don't see this effect. You don't see the spitting out effect so much when you're looking at a light source this way, because it spits it out in all different directions, right? So it won't mostly, you say, oh, well, it catches it and then just spits it back out. But it doesn't always spit it back out in this direction. It'll spit it out everywhere, right? And so that's why you see it more in absorption along one direction, and the other directions you will see it in emission. Does that make sense? Why do I care about this? Why does this matter at all? What am I talking about? How could you use this to your advantage if you wanted to know something? What could you learn? Yeah?
Detect the chemical physical composition of a star.
Yeah, you could figure out what stars are made of, the chemical composition of a star. You could determine whether there's stuff sitting in front of the stars that we can't see and what it's made of in terms of elements, etc. Yeah?
How far away can we use this technique?
You can use this technique all the way back as far as you can see galaxies, basically. As long as you have a powerful enough spectrograph and telescope to capture that light and do something with it.
And we do.
And we do it. So that's one reason why you want to have really big telescopes, so you can play this game and spread the light out. The more you spread the light out, the more light you have to catch, just because you're going to spread it out so you lose information. But in principle, you can use this on galaxies that are, billions of light years away, literally. Yeah?
I just wanted to ask, how does this work when used with gas giant planets and such?
Does this work with gas giants,
Yeah.
gas giant planets? In principle, it could, and the way it works there would be, for example, let's say you're looking at a star and it's got a planet going around it. Well, when that planet goes in front of that star, you've got all this light coming from the star, and some of that gets absorbed by the atmosphere of the planet. So in principle, you could try to figure out what the atmosphere of a planet that's really far away is made of using techniques like this, qualitatively, right? And you can look for things like, for example, O2. You see oxygen, O2, in the atmosphere of a planet, maybe there's life on that planet, right? The reason why we have oxygen on Earth, the reason we're oxygenated, is there's animals. Sorry, not animals. The animals breathe the oxygen, but because there's life. And that life creates that oxygen. Right? Yeah. Yeah, you had a question. Yeah.
If a star, say like we're observing a star, and it's moving towards or away, would Doppler shift affect how you capture the emission spectrum? Would it be shifted to one
Yeah.
direction?
So the direction that the planet's moving will also affect the Doppler shift. So the wavelengths will shift like this. So if you had a black body curve, the whole thing would be shifted, say, redward if it's moving away from you, and shifted blueward if it's moving toward you.
Okay, so this would also apply to the emission spectrum?
Yes.
The emission lines too?
Everything that's moving would all be shifted together. And in fact, this is actually how we measure the speeds of things, because what you see is you see the, like, say 3 lines that are associated with hydrogen, but they're not in the right spot. They're shifted off by some amount. Oh, well, that's the speed. It must be moving, and that's what shifted the wavelength. I'll talk about this in a later lecture. If people aren't following what I'm talking about, this is kind of a high-level question. If you don't understand what I'm saying, that's okay. I'm going to get to this stuff later in the course, so don't worry about it. Okay, I should probably get you a quick question, or does someone else have a quick question? All right, great stuff, great questions. So more generally, this idea of spectroscopy, it's not only used like in astronomy, it's used all over the place on Earth, right? So on Earth, historically, many elements were actually discovered using spectroscopy. There were spectral signatures that were seen, and that's the way people identified what things are made of on Earth. But a really interesting sort of historical fact is that the element helium was actually discovered on the sun before it was discovered on Earth. That's why it's called helium, helios. Right? It was seen in the spectrum of the sun before it was ever seen on the Earth. And eventually people did see it. It's a gas, they saw it as gas coming out of the ground at some point and took the spectrum and said, oh wait, this is helios. This is the sun. The sun's made of this stuff. Okay? So it's kind of cool, right? So this idea of spectroscopy allows us to discover things that are far away, that we could never actually send someone and hold a thermometer there or take samples of it and figure out what things are made of. So in a more sort of atomic way, what's going on, and this was mentioned before, but fortunately, nature has given us this kind of fascinating laws that are governed by quantum mechanics that make it so that atoms have sort of a quantized structure. And it's only because of this quantized structure of atoms that each atom has its own spectral signature, that it has its own barcode that then allow you to figure out what it is. So, this is a cartoon of a helium atom. And so, just to remind you, the nucleus has protons and neutrons. The protons are positively charged and the neutrons are neutral things. And the electrons orbit around way out here. But those electrons can only exist at very specific energies. They could exist at energy 1, which might correspond to sort of orbiting close to the atom, closer to the nucleus, or energy 2, which would correspond to orbiting grossly farther away from the nucleus, but nowhere in between those two energies. And the fact that they can only exist in those two discrete energies is a deep thing and deep mystery, and I'll talk about it later. But it's just kind of an observed fact now that we understand about nature. But because of this, it's because they can only exist here or here and nowhere in between. That's why the electrons like to absorb very specific energy photons, because they like to absorb photons that kick them up just to where they can go, nowhere in between. And so that, in fact, creates that spacing. And the associated energies with each of those levels depends on details of the atom, right? You can imagine you throw in another proton, then the allowed energies that the electrons want to sit at change slightly. And that changes that whole structure. And so in principle, that's why each atom has its own set of lines, its own barcode. Because once you add another proton, which is basically changing the type of atom it is, that changes the allowed energy levels that can exist. And so that changes the barcode that betrays those energy levels. So I talked about this before. If you have a gas cloud that's made of, say, hydrogen and helium, and you have a light source that shines through it, you pick up absorption lines. You see the gross spectrum from this light source, but then there'll be these dark bands, and those dark bands are betraying what that cloud of stuff is made of. And if you see that lines for both helium and hydrogen, you know it's made of helium and hydrogen. Or you might see a really, some other line that's like lithium. Okay, I see lithium in that thing, or whatever. So more specifically, if you have, if you now have an atom that's been excited, so you take, you have an electron that's been pushed out to its excited state, a little while later it'll fall back down to its ground state. And when it does, it has to give up energy. And it gives up energy by spitting out a photon. And that photon corresponds, the photon has a wavelength that's associated with the energy of this energy difference. Okay? So the energy gives you the wavelength. They're interchangeable, remember. So because I know this energy difference, that gives you the wavelength of the photon, so that gives you where that line is in that spectrum, or that absorption is, or that emission line. Vice versa, if you have an atom that's in the ground state and light comes towards it, it will ignore a lot of the light. Only the light that has that magic wavelength that lets it jump to where it wants to go will be absorbed. And that's that specific wavelength of that absorption. And like I said, if you add, say, another proton to the nucleus, that will change the energy difference here. And so the type of light it wants to absorb will change. But more or less, the only thing that's governed by is the type of atom that you have. So if you know the type of atom, and there's a very specific set of rules that tell you what lines it wants to absorb, or what type of light it wants to absorb or emit. Does that make sense? So, you know, this is sort of like maybe really annoying to you when you're having to memorize energy levels or whatever in chemistry class. Who's done that? I assume who's seen this stuff before? You must have seen this at some point, grossly, that atoms have energy, electrons in it. Who has not seen this kind of thing before, I wonder? Okay, that's okay if you haven't, I just wonder. Okay. Okay, so good. I'm glad you told me that. So, is it making sense, roughly? No? All right, if it's not making any sense, you just come talk to me in office hours and we'll... Okay. So, the basic idea, just in a, you know, if you don't understand the details, the basic idea is you have a gas blob, you have light shining through it. If the gas blob wasn't there ignoring stuff, you would see a spectrum like this. But because some of the light is absorbed, very specific wavelengths are absorbed because the atoms like to catch those particular wavelengths. You get a spectrum out that looks like this with a dark band. And where this band is, in fact, where the multiple bands are, tells you what kind of element it is, because each element likes to absorb different light. Okay. So let's talk a little bit about the kind of thing, what we've learned about from doing this. Well, let me give you, well, there are slides in there, there are extra slides in there that I haven't gone over. You can go over them on your own time too, and we can talk about them together if it makes more sense. So I've shown you this before. This is just an example of some absorption lines. And in fact, this is a spectrum of the sun, I believe. And so you can imagine with a complicated computer code, for example, trying to figure out, okay, what combination of barcodes do I have to add together to make these lines look like this? And I can use them to figure out, okay, what do I have in there, right? So you've got a bag that, the analogy would be, you've got a bag, you don't know what's in the bag. There's some like oranges and apples and bananas, and they all have barcodes on them. And all you do is you stick your barcode scanner in there. You're not allowed to look at them, but you just scan everything. And you get 5 bleeps of bananas and 4 bleeps of apples and whatever. Oh, okay, it's got 5 apples and 2 bananas or whatever it is, right? So even if you can't look in the bag and pick it up and see what they are, you could use these barcodes to figure out what you've got. And these are your barcodes. So then you could then ask the question, what are the stars made of? What is the sun made of? And then by extension, what are the stars made of? Well, stars are made of mostly hydrogen, it turns out. Far and away, they're made of hydrogen. The sun is 98.5% hydrogen and about 1% helium. And everything else are heavier elements. And I'll talk about those heavier elements in a bit. So the sun is mostly hydrogen and helium. The person to really put this forward and really sort of cement this as the truth is a woman named Cecilia Payne, who around the year 1920 was doing spectroscopic decomposition of the sun. And this was early days in the history of spectroscopy. And so in some sense, she was a pioneer for using these kind of techniques to figure out the composition of objects. She was in fact the first person to suggest that the stars were made mostly of hydrogen. And this was kind of a big deal. No one really believed her at the time because it was known that the Earth was not mostly made of hydrogen. The Earth is far and away not made of hydrogen. Okay? And so the prevailing wisdom was, well, you know, the Earth is made of whatever the sun is made of. We're sort of the same thing. But she made this point that no, if you look at the spectra of the sun and of stars, you find that in fact, if you take this spectroscopy seriously, the sun is made of mostly hydrogen. It took many years for astronomers to accept that she was right. And of course, she was right. She's an interesting figure because she was the first person, not the first woman, but the first person to get a Ph.D. at Harvard Observatory. And quite a pioneer because back in these days, there were not a lot of women getting PhDs, that's for sure, right? So this is quite a big deal. She's sort of a seminal figure. So this is an updated composition of the sun. So like I told you before, there's lots and lots of hydrogen. There's for every 1,000 atoms of hydrogen, there are 98. For every million atoms of hydrogen, there are 98,000 atoms of helium, and then just a trace amount of oxygen, carbon, neon, nitrogen, and oxygen. In fact, if you go out into the universe and try to figure out what the universe is made of, what is the universe made of in terms of elements? And this, you can do this from looking at stars and everything. These are the most abundant elements in the universe, in order here. And they're marked here on the periodic table. So hydrogen and helium are by far the most abundant elements. And then we have oxygen, carbon, neon, nitrogen, silicon, and iron. Okay? It turns out that we now understand that hydrogen and helium are made mostly in the Big Bang. Those are elements that are actually generated in the very first few minutes of the universe itself. But everything else on the periodic table is generated in stars. Okay? So that includes the oxygen we breathe, the carbon in our bodies, etc. All that stuff is made in stars. The elements that are important for life are carbon, hydrogen, oxygen, and nitrogen. So it's interesting to look at these things that we know are important for life compared to the relative abundance in the universe. And what you can see right away is that we are very rare things. Very, very rare things compared to what most of the universe is made of. And if it weren't for the life cycles of stars that basically take hydrogen and then along the way eventually turn that into heavier elements, we would not be here. So, you know, if you start thinking then about, so I should say too that there's a couple different ways of thinking about that. So one way you can think about that is, boy, you know, we're just like the dust in the corner. You know, we're just nothing. We're just these, you know, we don't matter at all because it's all hydrogen and helium. We're just sort of this weird afterthought. But another way of thinking about it is sort of like precious, you know, diamonds, right? I mean, the rare elements on Earth are the ones that are worth the most, right? So at some level, life in the universe is a precious thing because it's composed, at least all the life that we know about, is composed of these elements that are actually quite rare in the scheme of things. Okay. So I want to then just close with this slide, which, you know, I was talking about the electromagnetic spectrum, and this kind of lays out, you know, what we do with light, how big it is, and the different characterizations of light. Okay. Here's the wavelength scale up here. Just so you can get a sense of this. You know, visible light is, where are we? Right around 10 to the minus 6-ish, or right in there. So you can see the rough size of, for example, radio waves over here on the left. Okay, this is football fields. Visible light is right in here, about the size of bacteria or so. And then X-rays are sort of the size of atoms. And so if you want to study atoms, atomic structure, and take pictures of atoms in any way you can, you know, maybe X-rays is a way to think about it. It turns out it doesn't work because it blows atoms up. But it gives you a sense of sort of the size scale you want to use to probe different objects. And as we talked about before, ultraviolet light is the stuff that's responsible for sunburns. Here it says suntan, but sunburn. For these kind of body screening things that you hear about that are canceled, sort of in this range, the sort of millimeter range-ish size, etc. Yeah, you have a question?
Does the size of the wavelength for visible light limit how small we can see things?
Yes, it does. So the question is does the wavelength size of visible light limit how small of things that we can see? Fundamentally, it does. So even with microscopes, there's a limit to how small of things that you can see with visible light because of these wavelength issues.
Right.
It doesn't. Visible light does not bounce off very coherently. It doesn't bounce off of things very coherently that are like the size of the wavelength of light itself.
Right.
So in fact, that's why if you've heard of electron microscopes, okay, electrons behave also like waves. This is this particle-wave duality of nature. And it turns out that the associated wavelengths of the electrons you can make them much smaller and still handle them and study things. So that's one reason why electron microscopes allow you to see things that are even smaller than you can see in normal microscopes. So yeah, it's a great question. All right, people are shuffling around, so I'll end now, and we'll see you next week. Oh, observatory next Tuesday. We have observatory night next Tuesday. So if you want to go out and look through a telescope and look at real stuff, that's Tuesday night. I'll send an announcement about it too.